soon, and my distinguished colleagues, my young friends, ladies and gentlemen. I'm very happy to be here to celebrate the International Year of Chemistry. In fact, there have been attempts to have something like this for several decades through the International Period of Applied Chemistry, but it was not successful. Somehow, Marie Curie's 100th anniversary for the Nobel Prize somehow made it possible to do this. In fact, when I used to be president of the International Period of Applied Chemistry, we tried very hard, but chemistry never gets the importance it really deserves in science as well as in society. But I'm glad at last we have a chance to say something about chemistry in public. I must first of all say that I did give a very preliminary version of this talk a few years ago. I've even forgotten how many, probably 10 or 11 years ago, thanks to Dr. Arunan of the IPC department, who may not be here, who had asked me to give a talk. Since then, I was asked to give a talk on this by the Chemical Research Society, so I have prepared a proper talk on this subject. And the Academy, when they asked me to give a talk on this occasion, I requested the Chemical Research Society to allow me to give this before I give it actually in the Chemical Research Society later next month. Well, I'm going to talk about physical chemistry. Of course, I would have even talked about the evolution of chemistry, but actually that becomes part of this talk. So I will talk about evolution of chemistry as part of the evolution of physical chemistry. In fact, in the 18th century, just go back 200 years, we did not know what chemistry was. In fact, for those who have read history of science, chemistry was in search of identity. Because at that time, for example, we did not know whether chemistry was part of natural philosophy. And those who remember history of physics and chemistry will remember Newton. Newton was in 17th century. And Newton wrote the Principia, the famous book, volume of Newton, came toward the end of the 17th century. But after that, Newton was a great physicist, but a very bad chemist. I hope if some of you have seen it, it's well and good. Otherwise, you must see volumes of Newton's writings on chemistry. It was all alchemy. He went on trying to make gold in the lab out of all kinds of things using the unknown recipes of Newton. But there are several thousand pages here written on that. It is in my college in Cambridge for those who want to see it. Right? I've always wondered how a great physicist like Newton do such bad chemistry. But that's the thing about chemistry. Chemistry is different. And we knew it was different even during the times of Newton, when he did not know chemistry. But all the people then said was, everything that is not mechanical is chemical, they said. Well, but unfortunately, you see, chemistry was isolated from physics. That was a very terrible thing. Because physics, here was physics coming with new laws of the universe, new laws which are universal, which covered all of the universe in some way or the other. But here was for chemists not knowing what to do. But it was the late 18th and 19th century, people in fact did not know what to do about chemistry. So I'll give you then there was a Nicholson who wrote a book called The Dictionary of Chemistry in the 18th century. I will read out what he said, what chemistry was. If anybody here understands what he has written, please let me know. Because I myself have not been able to understand what he has written. This is what he said is chemistry. We might define it negatively by affirming that every effect which is not purely mechanical is chemical. Chemistry as a science teaches the methods of estimating and accounting for the changes produced in bodies by motion of their parts amongst each other, which are too minute to affect the senses individually. And as an art, we should affirm that it consists in the application of bodies to each other in such situations as are best calculated to produce those changes. That was chemistry. I have not understood yet what he exactly tried to say, but that is how bad it was. And then came the first chemist of modern chemistry, Lavoisier. 100 years after Newton was Lavoisier. And Lavoisier, of course, is, as you know, he was beheaded during the French Revolution because of his close association with the royalty. Lavoisier was the first chemist. He was the one who talks about chemical combination. He said air was oxygen and nitrogen. He studied something about combustion. What is combustion? What is, a whole bunch of things. What is respiration and things like that. So, in that 1 century, between Newton and Lavoisier, chemistry had absolutely no parents. It was one of those terrible situations. But once Lavoisier came into the picture, people started to guess what chemistry could be. And it was only at that time, late 18th century, just around Lavoisier time, the first journal of chemistry was started. It was by Berzelius, the great chemist. In 1800, Berthollet, he said chemistry has something to do with molecules, concentration, not molecules, compounds. And then, of course, the big thing that happened in chemistry was Dalton in 1803. For those who have forgotten, Dalton was a school teacher in chemistry, and he was the first one to talk about the atomic hypothesis. And we had a very tough time. I'll come back to that later. And in 1830, chemistry was considered as one which treats composition of substances and their relations to one another. So chemistry was different from physics, they said, for the first time properly made it. This is the history of chemistry. But the reason I'm giving you this is, Dalton, who gave the atomic theory, was a chemist. And we had a very great difficulty, as I will show later, with physicists who would not accept the idea of atoms. It took a very, very long time, several decades, before physicists said there was anything called atoms. The chemists who went on saying atoms, atomic theory, and the universal constituent of matter, chemists went on talking about it since Dalton. But what is interesting is, history of science is very always, he was a 19th century chemist. Remember, in late 18th century, he was a very young boy, we just started to work in a laboratory. He followed Humphrey Davy, who was a well-known chemist, who had discovered sodium. And I don't want to give the history of Faraday today, that would take me too long, but here was Faraday eventually, after 3 years of schooling, becomes an assistant to Davy and starts doing experiments, goes with Davy all over Europe, watching Davy doing experiments and talking about experiments with other scientists, other chemists in Europe, and when he comes back, Davy had to give him a job in the lab as a superintendent of the laboratory. Here was a boy without any formal education starting doing experiments. He did so many experiments that amazes me even now. In fact, I was amazed that somebody even confused him to be a physicist recently. He was a professor of chemistry, Fullerian professor of chemistry. Davy was a professor of chemistry. He followed Davy as Fullerian professor of chemistry. There is no question he was a chemist. Physicists have called him a physicist. Electrical engineers have called him an electrical engineer because of his discovery of electricity. That is a different matter. The reason that is amazing is, it is particularly young people who think about that. I have always thought about that. How did Faraday think of all those great ideas? Imagine it was in the 19th century, long, long ago, when no electron was known, atoms were not properly defined, atomic structure was not known. Forget, no electron, but electrons had not been discovered. Electron was discovered in 1897, don't forget. And how did he do all these experiments on electrolysis, liquefaction of gases, magnetism, diamagnetism, paramagnetism? These are the words coined by Faraday. The word permittivity, coined by Faraday. And he was the first one to make nanoparticles of gold in the laboratory in 1857. How did he do that? This is the kind of mystery. I leave that question unanswered. It is for young people to think. I think of it all the time. There must be something called intuition, which is beyond knowledge. It's beyond libraries and internets. Because they are the people who don't use the internet and library will make major discoveries. And Faraday showed that. Faraday had no formal education. There was no history to go to in science. There were no background lessons given in quantum mechanics. There were no professors teaching him. But he got a completely new idea in magnetism, electricity, discovered electricity, laws of electrolysis. How did he give laws of electrolysis? Without knowing there is something called an electron. Electron is required. Today you go to a classroom, they use an electron to teach electrolysis. But then there was no electron. Fantastic. What is interesting is, the reason I am giving you even these 2 minutes of Faraday is because this is the first time physics and chemistry got together without knowing. Our problem was how to imitate physics, how to be close to physicists. Chemists wanted to do that, they didn't know how to do that. And here was Faraday. Very naturally he did that without any direction, no instruction. Nobody told him you should combine physics and chemistry. He was actually the first physical chemist for the world. First chemical physicist for the world. In fact, there was the famous Faraday Society, I used to remember that for years, which was created for physical chemistry much later. I will not go on with Faraday, I'll come back. We just produced you all the wonderful things Faraday did. He even gave the idea of a field theory which Maxwell and many others worked on later, and here is the Faraday was only a chemist. Okay, I'll come back to, again, late 19th century. The first experiment in chemistry, like Bunsen was the one, we all know Bunsen, flame and all that. He's the first one. He worked on physics-chemistry interface, and he's the one who built a spectroscope. He worked with Kirchhoff. I hope you all know in optics, Kirchhoff, spectroscopy. He worked with Kirchhoff, and Koch and Landau, for all his students, are the ones who started saying, we must somehow relate properties of molecules or compounds to physical properties to something in their behavior. Then came law of mass action, Gutenberg and Wahl. I will come back to that maybe later. I saw Bunsen's picture because as a spectroscopist myself at one time, I always remember Bunsen, what a great man. How did he build all? He built all the instruments in the lab, by the way. There were no spectrometers available commercially in those days. Then came 19th century, Lothar wrote the first dictionary of modern, in fact, it was not dictionary, modern theory of chemistry, where he said the following: it cannot be denied that by the acceptance and the development of the atomic theory, chemistry became more and more estranged from the really related science of physics. The atomic theory separated physics and chemistry. And many physicists don't know that. They think atoms are theirs, but they're not. Chemists who really had to fight for that. Okay, the provinces of the two sciences were more sharply defined. Each discipline pursued its own path, and the portions common to both remained untouched. Unless, as was frequently the case, they were appropriated by chemistry alone. So chemistry had been found. Physicists will never touch them. Just like here, no physics department ever hires a chemist, but we chemists hire physicists. It's always the case. Chemists have always been very magnanimous. And chemists were never tolerated by physicists. So chemists had to define their own area all the time, but though it is physics, and say it is chemistry. So that was that's how the beginnings started. I will tell you that when Gibbs started beginning of thermodynamics, but what I say is not based on my opinion. That is the way when you read the history of science, you get this feeling how chemistry was an orphan and had to find their identity, particularly what we call physical chemistry. That is the worst part of it. Physical chemists were the ill-treated lot in chemistry for a very long time, and even now continue to be ill-treated in most places. The history of modern physical chemistry started with Ostwald. He didn't get the first Nobel Prize in chemistry, which he should have got. I will come back to that later. But he got a Nobel Prize in 1909. Please remember his face. He was the biggest name in chemistry and in physical chemistry, because though he may not himself done everything in so-called physical chemistry, he really fathered the subject. Literally everyone you know in chemistry worked with him. Every physical chemist of the world worked with Ostwald. I have gone through his work. He got his master's thesis in the year 1877, University of Dorpat, wherever that is. But he said after the MSc thesis, this is a terrible chemistry. Chemistry is in a very bad shape. Chemistry is in need of reform. Many of us say even now, chemistry is in need of reform. It will always be in need of reform. He said that. Then he was working in Riga for 23 years. He's in Russia, it was in the Soviet Union, now it is somewhere else now. It is one of these Baltic countries. Leipzig, he later went to 1887. I will not give his history. He was a professor there for a long time. What are the things Ostwald did? Ostwald diffusion law, conductivity and infinite Ostwald ripening, degree of dissociation, a whole bunch of things. And I will be dealing with Ostwald and his students, mainly Americans, who changed the subject of chemistry later. Ostwald's dream was, this is the beginning of the lecture today, evolution of physical chemistry. Ostwald's dream was, we must do something about physics and chemistry together called physical chemistry. We must do something about it, and his dream was, this subject will bring together physics and chemistry and mathematics. He himself was not a great physicist, he himself was not a great mathematician, but he always talked about it. He always talked about how it is very important for chemists to learn physics. And he was very, very particular that everyone learned physics. And then physical chemistry, he said, is a subject of the future. In fact, he says, what is physical chemistry? He said, at that time, that is in 1800 something, he said, the physical chemist studies the reaction and not the end products. He studies the reaction qualitatively and quantitatively with specific reference to factors such as concentration, temperature, solvent, pressure, electrical stress, time, and so on. He correlates his facts and draws conclusions from them so that it becomes possible to generalize from one reaction to all other reactions. So he had his own idea. This is what he said about physical chemistry at that time. Then there was another person whose name you should all remember, two great fathers of physical chemistry, was Van 't Hoff. You see, again from 19th century, he died only in 1911. He is the one when he was a young boy revolutionized chemistry by saying carbon has its four valences directed towards the corners of a tetrahedron. The tetrahedral carbon was his idea. He was then teaching in a veterinary school, teaching chemistry in a veterinary school, and this is Van 't Hoff. It's the same Van 't Hoff who talked about tetrahedral carbon. What are all the things? How? You know, it amazes me. You please read the history of chemistry and just chemistry, what started. You will be amazed how even today we teach these things, and they were all done so long ago. Osmotic pressure. He said gas law applies to osmotic pressure. You remember the I comes, I'm sorry, it's not electrolyte, non-removable. Free energy. RT log K is equal to minus whatever the free energy. That is what we use for equilibrium constant even now. That is what we did then. Most important is always Van 't Hoff's isoform. D log K by dt cubic. And then idea of the rate of a reaction. dC by dt is K C to the power n, where n is the order of reaction. How did he do that? You know, even now when I look at what he did at that time, it amazes me that to think of that in the absence of any literature, and that is Van 't Hoff. He was another great man of that time. Then again in 1974 came another great name called Svante Arrhenius, Uppsala in Sweden. Very big guy, huge guy, big eater and all that. He did to eat a lot. And he decided that he was going to be a thesis, and that these two professors were very bad professors. Many of them around. Who don't write stupid problems, who don't identify themselves as students. He is actually very bad professors. They should be professors. But he was that time. The reason that is important is that played a very important role in his life. He did this theory of what he called the electronic dissociation. I've told this story before, once more I'll repeat it, but those who have not heard me. He wrote this huge thesis. It became very big. It went on, became bigger and bigger. It became so big, by the time it became 4 copies, he could carry them. Then eventually he does carry them like that, apparently from third history, and dumps it on the tables of the examiners. And the examiners actually use the very filthy word. I don't want to use it in a public, very bad word. What is all this crap? That's what it amounted to. What is this your problem? And he said, this is my theory, electronic dissociation. They said, they didn't want to give him a degree, PhD for the work. And so, since he had written so many things of it, as an observation, at least as an observation PhD, there was 4 degrees, same as B, C, and observation. None of the 4 were the doctorate, look at it. There is no fail, which did not entitle him to teach in a university or work in an industry. So that he can be called doctor, but cannot use that degree for any job. And that is Arrhenius at that time. On 19th February 1850, and because this man changed many things in chemistry and science and so back. He didn't know what to do. He writes to Ostwald. Ostwald actually is like a father to everyone. Please do something. Ostwald said, I will let you in there. But no, nothing, no scholarship, nothing. You can work with me. So for 8 years he was taught what nothing. And he was Ostwald. He did that. Arrhenius then meets Nernst, the famous physicist, the chemist, depends on what he called her. The case the physics, doesn't matter, because he revolutionized both the subjects equally in various ways. Nernst comes also to work with Ostwald. And Nernst and Arrhenius both work with Ostwald, and that was supposed to be the most brilliant period of any physical chemistry group. There are 3 geniuses working in one lab in Leipzig, namely Arrhenius, Nernst, and of course Ostwald. Of course, Nernst and Heath, it's very important to remember these stories. They are very close friends. They used to drink a lot. They went to every bar in the city. They used to go after girls. I mean, all kinds of things. Well, you know, don't laugh at it. There's nothing wrong. I mean, I'm not saying it's wrong. And, you know, I just said they did. They were really very, they were great in the town, right? They were known for that. They were very, very thick, right? Nernst and Arrenius. Because that relationship will play a role in science in a few minutes. And then, of course, by that time, Bichat had come with the idea of chemical equilibrium. And you see, these are the three argumentative grades of physical chemistry in Leipzig. That is when thermodynamics was starting. Heat is work at Bucky's heat, first of thermodynamics. I hope you all remember. And that is Nernst at that time. And then you see, Nernst, very genius, he was brilliant. Poor Ostwald, a nice man. He was like a great father to everybody. But he was not very good in theory. Nernst was a theoretician. And Nernst doesn't like Ostwald very much. Because Ostwald was like me, an ordinary man. Ordinary chemistry, but Nernst was a theory and all that. So he didn't think much of Ostwald. More than that, Ostwald made one of the first mistakes in chemistry possible. Ostwald does not accept atoms. You know, it's a very amazing thing. Here were like Dalton onward, 1803, chemists are championing atoms. Oxford says he doesn't believe in atoms. He went along with the physicists who were then talking about everything is based on energy fields. I hope you know the history of physics. Everything on energy, those fields and so on. But of course, much later things changed thanks to great names like Planck and others who started going along with the case. Now, it was at that time, at last, Arrhenius' theory of electronic dissociation got accepted by the world. And you know, at last, the Swedish people asked him, come back, we'll give you a professorship. They gave him a professorship. Here was a man without a job for a long time. And he goes to Sweden as a professor. And Nernst, he leaves Ostwald, goes to Göttingen as a professor. There are three famous professors of physical chemistry. Arrhenius, of course, was, I just show this to show you, we indicate this to show you. Though physical chemists were there, they used to do all kinds of things. I wanted to know, for example, Arrhenius. He's the one who's worked on cosmic physics. He used to do all kinds of things. The first one to talk about greenhouse effect. Greenhouse effect was an early paper in 1890 by Arrhenius. I hope we all know that. It's not a modern word. Many of you think, I think it was discovered by somebody in Delhi. I don't know who it is. Nernst. He went to Göttingen. Nernst in 1893 wrote the first book of theoretical chemistry. It's called the Book of Theoretical Chemistry. And that's when he discovered the famous electric lamp. I hope you all know the history of it. He made the electric lamp, which everybody started using, bright lights for the first time. And of course, Nernst distances himself from Ostwald because of atomism. Mainly because atomism is something Planck did agree. But then, of course, came Boltzmann, Planck, who all said, it's very important, don't do this. A lot of people start accepting atoms in physics as well. At that time, it's amazing history. See, science, what has Nobel Prize to do with science? This is something, this is the one. Nobel died in 1896, you see, and they created the Nobel Foundation, and Arrhenius becomes the most powerful man. He actually decides everything that happened in the Nobel Foundation. By that time, he had become famous. So here is a man without a job, with a failure for a PhD, now controlling the entire Nobel Foundation. That was very important in science, you see, because Arrhenius, at that time, Arrhenius and Nernst also far apart. Arrhenius and Ostwald, Nernst and Ostwald, they didn't have very good relations because not because of Ostwald. Ostwald was a very gentle, nice man, but they didn't agree with him. What happened was once Arrhenius goes to Germany to visit Nernst, and Nernst says, you know, he is just like in front of a Tata statue, there are a whole bunch of Nernst lamps working, and suddenly, see my lamps, he says, and all the lamps, the fuse blows out. And then, you know, Arrhenius, this huge guy, laughs like a hyena. My God, you and your lamps, he says. And you know, Nernst being a real German, never excused himself. You know, that is a bad thing to do in public, laugh at Nernst on his lamps, about his bad lamps. So, they really, so, when the first Nobel Prize was to be given in 1901, this is a story of physical chemistry. If I were the chairman, if I were Arrhenius, I would have given to Ostwald. Because he was the really man who, I'll tell you why, in a sharp why. He didn't give it. Well, again, Arrhenius said under no condition should Ostwald get it. He gave it to Van Damme. Van Damme is the first Nobel laureate. The first Nobel laureate in chemistry is a physical chemist, Van Damme. And then, of course, many number of you, Fisher got in the organic chemistry. In 1903, he was about to be given to somebody, but Arrhenius himself got it, so he took it. And you see, Arrhenius got the same year as Curie's got it in 1903 for radioactivity. 1901 is oxygen, and of course it goes on until 1909. Poor Arrhenius, he thinks that Ostwald should be given this. And he gives him the Nobel Prize in a subject where he had done the least amount of work. It's very interesting. It's a way of insulting a man. It is like going to a very good spectroscopist and say, I'm going to give you something for something he had done, some third-rate work he had done earlier. It is like he gave him for catalysis, which was a very small. Well, then you see, that was the time, early 20th century we have come to, late 19th century. There are two types of physical chemists. Ionists are these, the electronic dissociation, ionic conductivity, Arrhenius and all that. Or the people who do dynamics of reactions, kinetics, how, and so on. There are two types of physical chemists. Physics and chemistry, math and chemistry got combined. The first time a journal called the Institute for Physical Chemistry was jointly edited by Ostwald and Van Damme, only late 19th century, 1887. The first physical chemistry journal. But physical chemistry was a European subject. Not even a European subject, it was a German subject. But everyone who wanted to learn physical chemistry had to go to Germany. But all the big names of modern physical chemistry were trained in the labs of Ostwald and Van Damme, particularly Ostwald. Low in 1889, Arthur Noyes, the great man, who went from there to MIT, later Caltech, to the head of the department, who was the godfather of Linus Pauling. Bancroft, the catalysis man in Cornell. Coggeshall, Walden inversion. Richards, atomic weight in Harvard, he went to a professor to Harvard. Then Lewis was then, I'll come back to Lewis later, student of Richards, but he later went to Ostwald, 1900, then went to Berkeley to create the chemistry department. The Indian connection I showed, McBain, who became the first director of the National Chemical Laboratory in Pune, did also work with Ostwald in 1900. Very interesting. And look at there are many other names like Donnan membrane equilibrium, again student of Bancroft and both Bancroft and Ostwald. I'll come back to that. You see that Donnan was a teacher of my teacher in Benares, that's Professor S.S. Joshi. So Donnan was my academic grandfather. Ostwald and Van Damme both are academic great grandfathers of mine. Ostwald had his legacy, learns, Arrhenius, and a whole bunch of things. But he had a lot of problems with other chemists. Other chemists became very intolerant of physical chemists. Even now they are. It's very difficult. In fact, when I got the August von Hoffmann medal this time in Germany, I was telling Professor Krishnan from Germany, all the chemists said, how did you get it? Normally he's only going to organic chemist. They said, how did you get an organic? No, even now that's the case. Well, it was so bad. Those days, the situation was pretty terrible. Here was Ostwald with the Nobel Prize. His salary was about 50% of that of the professor of organic chemistry. The professor of organic chemistry was not such a great organic chemist. He was Wislicenus. Do you know anything he did? I don't remember anything that Wislicenus did in organic chemistry. But he was the head of the department. He said, you are a physical chemist, Nobel Prize and doesn't you get only 50% by chance. So we physical chemists have always been at the receiving end, so it's not real money receiving the other thing. The Ostwald was not very well. Early physical chemists in the US, it's very important, physical chemistry started growing. Bancroft, he's the one who started working on phase rule colloids. He was an anti-mathematics. He wrote an equation, y equal to mx plus c. He said, what is this theory or anything, he would say. And he would not like anything like an equation in a straight line even. Everything was given lots of facts and tables. And then, of course, Jones wrote a book on the solution to the matter. Then Richards, who went to Harvard, did atomic weights. Harrington Daniels did kinetics, and so on. Don't forget, only in 1963, 16 to 25, that period, X-ray diffraction became, I'm trying to remind you what the period is. X-ray diffraction just came around that time. And Debye theory came in 1923, just around that period. Physical chemistry was started by Bancroft when he went to America. He would only accept papers on base rule and colloids. Everything else he said is not physical chemistry. And anyone who had an equation, he would be very unhappy with it, so he would reject the paper. I'll come back to that later. But amazingly, in 1896, 5% of the papers in JSC were physical chemistry. By 1925, 27% became. And people start teaching. The MIT had produced by 1925 5 people in physical chemistry PhD. Very few, 4 people in Berkeley. Very few PhDs came in the subject. And of course, there was what happened up to that is what about other countries? I just went to Britain. Britain didn't take physical chemistry too well. There was one Ramsay. The reason I mentioned Ramsay is very important to Indian social science. It is his report that created this institute, his report to the Royal Society. But Ramsay was the only one who accepted the idea, something called physical chemistry was there, the idea of ions and all. He was the first one to use the ion in Britain. Amazingly. Cation, anion, things like that. In France, they didn't like the talk because it's all German, see. They didn't like Germans doing physical chemistry. French people, they started their own generalization in physics, but they tolerated physical chemistry, but not much, not too happy with it. But then, of course, Arrhenius was doing many things. There is a time when Ehrlich started, the famous Ehrlich in immunology. Arrhenius contributed quite a bit to work in immunology, using physical chemistry. But, of course, again, Arrhenius doesn't like Ehrlich, so it doesn't allow him to get a Nobel Prize until 1908. But 1906, third law was proposed by Ernst. I hope you all know that. Hit theory. And here I actually analyzed it going to the original papers. By the way, don't forget, 1906, Nobel Prize was given to J.J. Thomson for discovering electron. Ernst, in the same year, he discovered third law. 1908 Nobel, chemistry Nobel went to Rutherford. Atomic structure. This is the third law of thermodynamics. When T goes to 0, the free energy becomes equal to enthalpy. That's what Nernst said. Actually, Nernst was a bit dishonest. He has seen all this data actually done by Richards and G.M. Lewis in Harvard. He looked at data but never acknowledged it. But his conclusion was based on the data he had seen at Harvard. There's no doubt about that. Everyone seems to agree. But anyway, he did come with this law. Of course, it's completely wrong, not completely correct, put it that way. Slightly wrong, but we'll come back. Then was around that 1885 was the great chemist J.M. Lewis in the United States, and he got his PhD under Richards, but Richards was a terrible professor again. He did not allow any original thing. Anything he wrote with an equation, Richards also would like. He also was against equations and things like that. And for PhD thesis, he is the first man to write, I hope you all know the equation of free energy with using heat capacity and all that. First, that is part of Lewis's PhD thesis. And when that went to Journal of Physical Chemistry, Bancroft said, you think by writing the equation you solve all chemistry? He wrote a very bad letter to J.M. Lewis at that time. Anyway, Lewis, 1897 discovery of the electron. You see, just then he had got his bachelor's degree. And actually he wrote a paper called Electrons and the Molecule at that time. But unfortunately, Richard said, for everything you are dreaming, it's all nonsense. For everything you call it's all nonsense, trash. So he wouldn't allow him to publish it and all that. So Lewis never forgot or forgave Richards for that. And he wrote his PhD thesis, free energy, gave a new equation, and of course, used how specific heats are involved, a whole bunch of things. His equation was an improvement over Nernst. In fact, his animosity, Nernst's animosity with Lewis started there, just after the PhD thesis of Lewis. In PhD thesis, he was very critical of the way Nernst wrote his equations, and many things were partly correct, partly not correct. And when Nernst saw that, who is the young punk from America writing all these things, being a German, old Russian, Nernst didn't like all that. So in the meantime, he goes to Ostwald and Arrenius. Lewis goes there. He doesn't like Nernst because Nernst was very difficult to work with. He would say, in Germany, he would say, every day he would come to the lab and say, you have got any new numbers? He would call them. And the students would are supposed to show him some new data and all that. But Lewis didn't like that type of doing research like that. He was not. So he was back to Harvard after all that. as an instructor, but Richards was so oppressive head of the department. Okay, there must be many heads of departments here. I hope they are not as oppressive. I want the young people to come with new ideas. I had a very oppressive early period right in this institute, so I'll never forget that. Very tough time here. So I hope things have changed. But Lewis and Richards fall apart. You know what he does? This is a story for physical chemistry, very important in physical chemistry, because he reads a New York Times advertisement looking for a person to head the Office of Weights and Measures in Philippines, in Manila. Superintendent of Weights and Measures in Philippines. Lewis applies for the job and gets the job as Superintendent of Weights and Measures, and he leaves Harvard and goes to Philippines. And of course, the only book he took with him was Nern's book on theoretical chemistry. And then he comes back from Philippines. What Philippines did was, he started smoking cigars like mad. Toward the end of his life, he should smoke about 30 cigars, 25, 30 cigars a day. Big cigar smoker. That doesn't matter. So, in 1907, he wrote these outlines of a new system of thermodynamic chemistry. And in 1912, he came to MIT, by the way, from Philippines. He didn't want to go near Richards, who was in Harvard. 1912, he was appointed professor in the department at University of California, Berkeley, and they built this great department, probably the world's greatest chemistry department even today, from Lewis' time. And it was Lewis who joined there in 1912. And then, 1914, Richards was given a Nobel Prize for atomic weights, but 1916, at last, G.N. Lewis wrote his first paper on atoms and the molecule, the idea of a chemical bond. That was the first paper on chemical bond written by a physical chemist, by any chemist, 1916. Then came in 1921, the idea of ionic strength, de Broglie theory, the idea of activity and fugacity. Arrhenius got very angry at him because the idea of activity he thought was his, but he never defined what activity was. He always called it active state, Arrhenius, but he gave activity, he used it in equations. I hope you all know in thermodynamics what activity is, fugacity, that. And he even wrote a small monograph called Valence and the Structure of Atoms and Molecules in 1923. And the book, the famous book that made thermodynamics part of chemistry, was written by G.N. Lewis, the Thermodynamics and Free Energy of Chemical Substances. That was G.N. Lewis. And just for the heck of it, I'm showing you the way he discovered the octet rule, a whole bunch of things, the way he wrote chlorine molecule, or oxygen molecule, you see the double bond there. It's really very interesting in 1916 paper of G.N. Lewis. And 1925 onwards, thanks to Lewis, thermodynamics becomes part of chemistry. Lewis says, idea of a chemical bond, people said, your idea of a chemical bond is much too quantitative, it talks about sharing of electrons, forming a bond. Then he said, no, theory will come. I said, quantum mechanics had not yet come, don't forget at that time. So, he said, theory will come, better theory will be done, he said. And chemistry has suffered, particularly physical chemistry, that Schopenhauer's famous 3 stages of truth. I hope you all know that, young people should remember, if you really come with a new idea sometime, which many of you I hope will come with new ideas, you will never be accepted at the first stage. Second, it will be ridiculed. You will say it's all junk. All your colleagues will talk about, laugh about it. And third, they will say, you are so self-evident, what is so great about it? So that's the third. So Schopenhauer's truth, Lewis suffered that in his life. His idea of a chemical bond never got accepted. There is a very, very sad story of physical chemistry. I will tell you in a minute. Lewis' style of research is very important for those of us, like, I love this institute, so whatever I say should be taken in that trial. Now the criticism, because I am part of the institute for 60 years now, so don't ever take that criticism. But style of research, now young people, faculty members, there's a lot of money for travel, of course they travel. They travel a lot. And of course in my time there's no money for travel, you couldn't go anywhere. If you want to go Delhi, the unreserved third-class compartment for 3 days, I did all that, my God, so you plan to trip 1 day, great travel. So today it's very easy to travel, so there are a lot of people travel. But Lewis' style is very important. It's a big lesson for all the good scientists here, young scientists. He never went to Europe running around, giving lectures all over the place. More lectures nobody wants, but we want to give it. So like I'm giving here. So, lectures on that. Lewis never left Berkeley. Because the analysis of life, he didn't believe in that. But what his power was not in giving lectures. He's a very bad lecturer. He's an outstanding writer. His English language cannot be improved on. I think the greatest writer of English, probably science has ever known. I'll come back to that maybe later. Okay, and he says, what is physical chemistry? That is the time he said, physical chemistry, he said, is anything that is interesting. I think that's a wonderful definition for physics, chemistry, physical chemistry. I think if you find interesting subject is interesting, do it. And then, of course, he gave the final statement of third law, because third law of that's wrong, because F equal to H equal to F is equal to H, 0, T is not right unless F is equal to 0. The entropy concept was added on by Lewis in this statement of Lewis, third law. And in the joke actually said that Lewis third law at that time. Around that time, Lang was born, there, maybe not 3, but 2 years later, 4 years later, 2 years later, he got all this. He also went to not to Ostwald to work. I can see myself. There is the drums shouting to that. There are the numbers. And he didn't like it, but he got a PhD at it. And he got a small job at Stephen Institute of Technology as an instructor of $1,200 a year. And he wanted $100 more, $20 more. And they said no. And so he left and because he went to General Electric. That's where he worked at the tungsten bank, surface testing, monolayer, diamond project film, and so on. And written stolen from Lewis. That is very interesting. He gave the octet theory, Langmuir octet, even though books like textbook Langmuir. It is a very great insult to Lewis. Lewis, the theory included octet. You see his structure, not octet, isn't it? And Langmuir went on using the whole octet thing is very important. And people were talking about them and went there. Of course, Lewis gets very mad. He writes in American Chemical Society, this is very wrong. This is all in my, already octet idea is in my, look at the figures I have written and all. But then, amazingly, Langmuir writes back to Lewis. I'm sorry I have done all this. I will not publish hereafter anything more on this. In your subject, I'm sorry. He apologized. But people don't know that. They still call it the Langmuir object. I don't know why. It's actually Lewis object. He was a very great man. In his own right, surface chemistry. And Lewis had done many things. Don't forget, the word photon was proposed by Lewis. Lewis did a lot in theoretical physics. I just wanted to know how physical chemistry could shape. He wanted to nature of light, theory of radiation, even published papers on relativity, not great papers, they're all very bad papers. That's not what I see people say. But he's down with all theoreticians and he's really a physicist in a way. Of course, Langmuir did many things, but they were very different. Langmuir was very small, very well dressed, he knew French, he would go to Europe in lectures, exactly after he was sitting all the time in Berkeley writing papers. I like Lewis' style actually, but Langmuir succeeded better than Lewis in many ways. And of course, then you see A.A. Noyce got a PhD with Ostwald, went back to MIT, then he went to Caltech as a professor. People called the Caltech period King Arthur and his court, Arthur Noyce. C.N.R Rao, the same time went to Berkeley, they used to call it Louis Circus, in the famous history of chemistry. The reason it is important, at that time, Linus Pauling entered the scene. Linus Pauling, 1925, Caltech, under Noyce, not under Noyce, Noyce was the health department. He gets his PhD degree in chemical engineering. He's not a chemist. Pauling. And then he wanted to do chemistry, then he went to Berkeley and Caltech. Berkeley was 3 days late sending a letter, otherwise he would have gone to Berkeley for his PhD, but he went to Noyce. He said, Noyce said, you work on X-ray diffraction. He said, just the X-ray diffraction I've done. He saw many structures for his PhD under Anderson, and then he had to do his doctorate. This is a very important story for all of us. In my life, I've had something similar experience with my students. We have had students all day, until they do his everything. You don't want to do after PhD. He was about to go to Berkeley. He was offers in middle age, I went to Berkeley. He was about to go there, and Noyce said, don't go to Berkeley. Go to Germany, learn quantum mechanics. And Noyce said, the future of chemistry is lying behind with quantum mechanics and theory. So you become that. So he sends him. He said, I don't have money. Actually, his boss says $1,000 to Linus Noyce. Because really he's a academic father. And he said, $1,000, go with your young wife, but just Linus money. And go to a at that time, Solomon felt that students like Heisenberg, Max Born, Wolfgang, much later, Hans Bethe, Heinz, they're all friends with Solomon. And Linus Pauling goes to Somerville to go to work. And that changed again. That one change made the Noyce, making him go to learn quantum mechanics. And he was come back, he wrote the best paper. Theory of electrons, atoms and molecules. And published this in Procedure also, a single author paper. You must read that. And this was really seen by people like X-ray diffraction. Who is this young stupid fellow from America writing all these papers? British people never liked all this kind of thing. Those days. Linus Pauling wrote the first paper of quantum mechanics applied chemistry. And he comes back to Caltech, and the Caltech offers him assistant professor of physics and chemistry. But what is amazing is that the head of the Caltech president was Millikan, famous oil drop Millikan. And he did like Pauling in time. He said, who is this chemist talking like physicist? He talks about quantum mechanics, he has no business. So by the time he came to join the Institute of Caltech, his friend was only section was on chemistry. He said, what about your letter said physics and chemistry? No, Milken removed the physics class that he doesn't want to do it. So Milken didn't want it, so Pauling was only, he was very upset actually, because in fact Pauling writes beautifully in the time, although historically, atoms and molecules should have been physics or chemistry. I think chemistry is the right place he says, not physics. You really don't talk about that's Pauling writing at that time. And he becomes a faculty member in 1928 at Caltech. And then like he started quantum mechanics, with the famous Ibrahim Wilson, the whole famous spectroscopist, Ibrahim Wilson, he wrote the first book on quantum mechanics. The first book ever written quantum mechanics is by Ibrahim Wilson. My textbook, I was a PhD student in fact. The other day I told you, some years ago, I met Leon Letterman, the Nobel laureate. He said, his first textbook is quantum mechanics, the Linus Pauling's book. He says, oh, physical chemistry changed. Because one thing made Linus Pauling learning quantum mechanics. But then I'm going to just give you history again. Julian Lewis, 1933. Deuterium was discovered by Harold Urey in Columbia University. And immediately, of course, G.N. Lewis makes heavy water because that is the way they used G2O. By that time, oxygen isotope has been discovered in Berkeley and so on. And then we see they had found this terrible thing. Where do you publish papers in physical chemistry? I had this problem when I was young. Whenever I did work on chemistry materials and solid state chemistry about 50 years ago, there was no journal. Inorganic chemistry, well, it's not inorganic. Physical chemistry is not physical chemistry. It was a very practical problem. Physical chemists started facing they didn't have a place to publish their papers if they had quantum mechanics in it, for example, or bonding in it, or thermodynamics. So there was a famous meeting between Lewis and Pauling. And they tried to play Prof. Will you change your journal of physical chemistry to include all of physical chemistry, or you only want colloids and phase rules? And he says, he sticks to the colloids and he said, no, I won't publish. Then went to American Chemical Society, into this, all kinds of things. I will not go to the long story. Then they said, enough is enough. These people decided to start a new journal with the Institute of Physics, not with the Institute of American Chemical Society. They called it the Journal of Chemical Physics. They appointed Lewis's student, Urey was PhD student, Urey. He was made the editor in 1933. And the best of chemical physics, because then the physical chemistry would accept papers in chemical physics and other. And the first issue you must see, which I have seen, where everyone, people find the areas of chemistry, Linus Pauling, G.N. Lewis writing on Arthur Noyes. Lewis again in the chemical branch, the first paper, and so on. And the whole bunch of other authors. 1934, again, Lewis was hit in the head. Again, Nobel was only given the Urey for deuterium, G2O was ignored. 1935, Pauling wrote his first book on quantum mechanics. In the meantime, Lewis started with Seaborg as a student, as an assistant. Lewis assisted, Lewis basis, the major contribution of Lewis. And then 1939, Pauling wrote The Nature of the Chemical Bond, the book. In fact, when he decided to write, he writes to Lewis, I want to write a book on Nature of the Chemical Bond. Lewis offers to co-author with him, but Pauling being a very selfish man, you may know, he is a shark. Pauling was a great man, but he's also a shark. He didn't want any credit to what anybody else except himself. So he wrote it himself. But he dedicated Nature of the Chemical Bond to Lewis. Then he sends a copy of the book to Lewis, and Lewis writes back to him. I have just returned from a short vacation, for which the only books I took were half a dozen detective stories and your chemical bond. I found yours the most exciting of the lot. I cannot tell you how much I appreciate having a book dedicated to me, which is such a very important contribution. I think your treatment comes nearer to my own views than that of any other authors I know, and there are very few places where I could possibly disagree with you, and those perhaps because I have not thought about the thing sufficiently. Lewis wrote to Linus Pauling. And great man, he was a great man, Lewis. Their nature, his birth of physical chemistry, you can see very close to that, 1930s. And then, the reason this is historically important is, 1951, the alpha helix was discovered by Linus Pauling. Of course, birth of molecular biology, that's what I say. But that year, after that, 1954, for those who may not know, I just went to the United States at the time. He was given a Nobel Prize for Chemical Bond in 1954. Wait, that long. From 1916 or 1920 to 34 years, chemical bond did not get into the chemistry. 1954, for chemical bond, Nobel Prize was given to Pauling. By that time, Lewis had died. Lewis died in 1946. So Lewis could have shared it anyway. What is the tragedy? Here is the thing about young people, please know. Here is the fundamental thing that revolutionized the idea of molecular structure, chemical bonding, that did not get recognition by the Nobel Committee or anybody until 1954. When I was doing my study, I had PhD work later. Stupid. And this is the thing. What happened to But anyway, eventually they gave the Nobel Prize. And I remember all the earlier records of the Nobel Committee. Oh, what is so great about chemical bond? I don't think it is important in chemistry. Nobel Committee saying that. It doesn't do it. Of course, partly maybe because Arrhenius was against it, Nance was against Lewis, so they didn't want him to get it also. That's another story I'll not be talking about today. Well, agents have changed, and I'll come back to this in a minute. Before I'm coming about to conclude, let me tell you, when I was young, I was doing a chemistry research in Benares. My teacher Joshi told me, I mean, very tough, actually, we were all afraid of him. Whenever we saw him, we would take other room. We didn't want to see him. Very difficult man. It's an old-fashioned DSE London and all that stuff. And he was a student of, I told you, Donald, who was a student of both Weinhoff and Ostwald. He did tell me once, you know, I'm Donald's student, you know, Donald's student of Ostwald. So you helped all this. I didn't understand that. Actually, I didn't understand what he said. Now, I'm preparing this lecture. Last 2 years, as I'm becoming 77 years old, I understand what it means. You see, I know who is my grandfather and great-grandfather. See, when you are young, you don't worry about it. The great Weinhoff and Ostwald are my great-grandfather. Donald, of course, was a great man. It was true. And then you see, I went to work with another person in America for PhD. He got PhD in line spelling. So Lali spelling is my academic grandfather. Fantastic. Then I went for a postdoc in Berkeley, and it was G.N. Lewis' student. And so G.N. Lewis is my academic grandfather. And G.N. Lewis worked with Darmstadt and Oxford. So they are both my academic grandfathers. See, you're all laughing. See, you can laugh at an old man, but it's very important. Science actually goes because we sit on the shoulders of other great men. All science has progressed because great men have discovered. We think we are great. No. You are great because you have used the greatness of others earlier. And the agents have changed. The modern progress of physical chemistry. Ostwald and Weinhoff, I put on the side these two names, two original physical chemists, two derived great physical chemists, and Ostwald and students. They require transformation, thermodynamics came, structure came. You take everyone like G.N. Lewis and all Burns, all the students of Ostwald, and of course then Arthur Noyes, student of Ostwald, Lewis, student of Ostwald, then came Collins, who was really academic father in day was Noyes, and many other actors. Pauling, of course, Hitler in London influenced to come with Bellot theory. Then Mulliken came with Hund, who was an influence of Hund came with molecular orbitals. Irene came with chemical kinetics. But I would not say they changed chemistry. They changed chemistry because of their contribution. The direction of chemistry had been set by that time. And they are the actors by and large, these big names are. I put them in smaller letters because of that. Leonard Jones in Cambridge, Popper got his PhD in Berlin, and then Popper Buckingham got his PhD. So all they're all my friends. But they're all much better. But Leonard Jones' potential. He was one of the earliest physical chemists of the world. But I didn't put it in capital letters like this because I don't think they changed the direction of chemistry towards physical chemistry. Now, Ostwald could not realize his dream. His dream was to make physics and chemistry together. Find something that was somewhere in between, and then he couldn't do it. His students did it. Noyes, Lewis, and their student, Linus Pauling. And so modern physical chemistry, in many ways, owes its origin to the great German masters whose students in America gave shape to the subject. Actually, physical chemistry became an American subject in a way. Even today it is. But it changed in the hands of the Americans, thanks to Lewis and Noyes, who created a new school of physical chemistry. You see, I told you that G.N. Lewis wrote English like nobody could. In fact, I never found any chemist who can write like G.N. Lewis. There may be physicists, I don't know, there may be others. So I would read to you the last few sentences of his preface for his book in thermodynamics, the famous book of G.N. Lewis that he published in the 1920s. What he says here is true of chemistry, of any new subject, certainly of physical chemistry. Only the perfection of a completed whole. We are impressed as by some superhuman agency. But sometimes we enter such an edifice that is still partly under construction. Then the sound of hammers, the reek of tobacco, the trivial jests bandied from workman to workman enable us to realize that these great structures are but the result of giving to ordinary human effort a direction and a purpose. Science has its cathedrals, built by the efforts of few architects and many workers. The story of physical chemistry, I think exactly, is what C.N. Lewis said long ago in his book on thermodynamics. Thank you.
We would all agree that we had such a beautiful talk and a feast to all of us, and we don't have enough words to thank Professor Rao. Just as a token, we'll have a bouquet offered to Professor Rao by Professor S. Chandrasekharan. And then Professor Ramakrishnan will propose a vote of thanks.
I'm sure all of you agree that this talk by Professor Rao was not only inspiring in terms of the historical content, but also in terms of the inspiration that it provides for young students in this audience. So I'd like to first thank Professor C.N.R Rao for having taken this time and come here and made this presentation for us. And then I would like to thank the Indian Academy of Sciences for having taken this initiative to host this lecture, along with the Chemical Research Society of India. And finally, I'd like to thank the Indian Institute of Science and the members of this for having come here to listen, and also for having provided this wonderful hall to listen to Prof. C.N.R Rao. With that, I'd like to invite all of you for having a cup of tea at the